Okay. Hi everybody. Can you hear me okay?
Yeah.
Okay. Can somebody be a responsible person who will nod when they understand me? Okay. So I see one. Anybody? Okay. You're just really far. Can you somebody close, please? No, roughly, so I can make progress because it's really hard to talk into the void. Huge thanks to Steven for shout out. Yeah, hopefully after this you will understand a little bit about how SIMD works just in general, and maybe you'll be able to write a little bit of SIMD code. Yeah, my first SIMD is actually a reference to an Eminem song. That doesn't matter. So what's this about, right? There are a bunch of talks online about SIMD. And most of them are like by somebody who is really deep into the subject, and they assume that you know everything about SIMD. They just like talk about their specific thing, like, oh, when we introduced C++17, we discovered this parallel guarantees, right? And because they've been writing SIMD for years and years, they kind of know what they can do with those guarantees. But I was looking at, but example would be something like Saxby, right? To go to the arrays, add, multiply them together, right? And in the meantime, there is strlen, and strlen is totally vectorized, right? There is sort in C++17 and 20 that is supposed to be vectorized. Like there is no existing implementation of that in any standard library shipping, but there is seek. You're supposed to get vectorized sort. So I looked at that and I was like, how does that work? And I went online. I spent a lot of time on Stack Overflow and in such places. I learned, I implemented much of that then. And now there's production implementations you can use for all of those things. So how good is strlen? This is, let's see how this works. Yeah. So this is for 40 bytes, right? I'm going to measure all of my sizes in bytes because SIMD depends on byte size. Like you have really big register, and it doesn't matter what data is in it. Like it can be ints, and then you have, let's say, 8 ints on my machine, right? Or it can be chars, and it's going to be 32 chars. But the performance is going to be roughly the same because it's still 32 bytes at the operation, right? So how good is strlen? Well, this is unfortunately is not showing very well here, but this is about, let's see, no, I believe this is about 30 something times faster. Like I'm gonna try to remember. Okay, I'm gonna be remembering numbers. Okay, then we go to 1,000 bytes, right? This is 1 kilobyte, and sorry, this is about 9 times faster. Yeah, this is about 9 times faster. This is about 30 something times faster. Can I get the number? No. And for 10,000 bytes, this is again about 30 something times faster, 31, 32 times. And the way they do it is they do it with SIMD. So a few disclaimers, right? Performance is tricky. Like there's a lot to know about hardware and performance and measuring. So to get like really good numbers, I know some of it. I might mess up something else. Everything I show will work on x86 and ARM, but I don't have any ARM measurements. I just don't have it set up in any reasonable way. And I can be opinionated at places. Can somebody nod? Thank you very much. Okay, so this is the plan. We're going to talk about what is SIMD and how do you get it. Thanks to Steven, we have a little bit of an idea of that. Then I'm going to show you strlen, and I'm going to show you everything there is to know about strlen, well, most things there is to know about strlen. And finally, I'm going to, on a high level, explain a few more algorithms. All right. So what's SIMD? How do you get it? Steven mentioned there is a bunch of extensions that you have. Like, so you have processors, new processor comes out, it has new instructions sometimes, right? There is new instruction set with new generations of processors sometimes. All right, for x86, you have those 16-byte registers. So for example, in my childhood, everybody wanted to play video games on Pentium 4. Pentium 4 had SSE3, right? So this is really old stuff. PlayStation 2 had AVX, so 32-byte. And this is like whatever 7 years old PlayStation 4. Like, so, and at the time it wasn't the top hardware. Most of the slides I originally did on a MacBook Air from like 2015 that had AVX2. So this is still like not top of the range hardware, right? And then finally you get into AVX 512. There is like a lot of variations. Some are more common, some are less common. Practically all of this is servers. Like there are very few laptops that's shipping today with AVX 512. Well, this is slightly changing. Sometimes they have a little bit. Anyway, then there's ARM. So Neon and ASIMD, like ASIMD sometimes is also called Neon, but basically this is ARM v7, ARM v8. So this is 32-byte and 64-byte ARM. For example, ASIMD is probably in most of your phones, and M1's is also ASIMD at most. Then there's SVE. There are two versions, not on SVE itself, but on how you program it. VLS and VLA. You can ask me later about SVE, but this is ARM server stuff. Sorry about that. ARM server stuff. So they are trying to deploy now. ARM is trying to muscle in on the server market, and this is how they're trying to do it. There's also some stuff on PowerPC, and there are WASM extensions as well. Okay. Which extensions you program against matter, as again Steven showed, and this is an algorithm from the library I maintain called Eve, right? And this is a standard version of remove, right? So we're removing zeros from an array. Like this is scalar code on the top. This is integer, 10,000 bytes of integers, right? It's a scalar version, and then this is SEC2 for AVX2 plane, AVX2 plus BMI extensions on my machine measured, right? And so you can see if you know specifically which extensions you target, or the better you know, okay, I can target more modern hardware, you can get more performance. So it's important to select appropriate minimum hardware. And once you find that out, like for example, you have the minimum something you're shipping, you should tell your compiler about it, right? The more simple way is to do March native, right? I'm compiling for this is machine I'm compiling, this machine I'm going to run on. You can also say, okay, I have at least IVX2, like this is something we do at work, for example. And then we can do runtime selection, which is very difficult. So basically, runtime selection is you test which flags are available at your runtime, and like, okay, if I have IVX 512 with all the necessary subgenres, I'm going to go there. The problem with that is ODR violations, right? As soon as you start writing some complicated SIMD code, you will have functions. And those functions you get compiled, and then you have two versions of the same function compiled twice. You try to link them somehow in the same binaries. That's ODR violation. You get undefined behavior. So this is hard. In Eve library, we recommend you do plugins. This is the same. So you have like a DLL compiled, and you try to load which one is available at runtime. Okay. So far, makes sense? Thank you. Okay. So we enabled with all the compiler. You can use SIMD code. Now we need to get some. Simplest way to do it is auto-vectorization, which is awesome, and that's the first thing I look at. It is great, but it's also limiting. On Clang specifically, it's great. You can get usually transform or transform reduce. If you can make your function look like a transform or transform reduce, you can get it vectorized likely. Yeah, if you do floating points, you might want to do fastmass on that file or on that function, because floating points, you cannot rearrange the computation unless you tell the compiler that it can do it. There are pragmas. All I have seen the pragmas do is act equivalently to compiler options. So basically, you can say fastmass with a pragma instead of compiler switch. That's it. I don't know if they do anything else. And finally, you can write intrinsics by hand, or you can write assembly by hand. Sometimes people choose different approaches. And this is what kind of we do. Okay, thank you. So with the first two approaches, you are like in a good place. You just write your Scala C++ code, and you don't need to know anything else. With as soon as you start writing SIMD as SIMD, you need to understand the programming model behind it, and it's sort of makes sense. So you have a 32-byte register, for example, on my machine, right? And you can interpret that register as any of the primitive types. So you can do chars, shorts, ints. You can do floats or doubles as well. It's no problem. And then you have like a list of million instructions, right? This is just additions, but additions might make an impression that they make sense. They don't. There are really crazy instructions that are designed for very specific things, or like maybe they're legacy extensions for legacy extensions. They can be useful in certain situations, but it's not obvious from just looking at it. And okay, using intrinsics is perfectly valid. If you have one platform you want, and you know for sure it's one platform you want, and like you need to just hack this one routine, go for it. I deployed recently base64 encoding in prod, written like by hand with intrinsics. Absolutely reasonable thing to do. However, yeah, so you just include imintrin.h on x86, you include armneon.h on ARM, and you can write intrinsic code. It's shipping with a compiler. There is a guide links like with description for everything. However, even if you do it by hand, you want to wrap it. Basically, to understand why, like there is a very popular library called SIMD everywhere. What SIMD everywhere does is you plug it in and it replaces your intrinsics for your platform with intrinsics appropriate for the current platform you're working, right? So it ports x86 intrinsics to ARM. It cannot do that efficiently. It's impossible to do that efficiently. But because people write a lot of intrinsics just directly in place everywhere, they use it, and then they leave it there and they have an efficiency and all this stuff. If you wrap your intrinsics in some higher level abstractions, you can then, like, you have much less things to fix, and they make more sense. And you don't have to wrap it yourself. We have a library. I believe this is the best solution, but I'm biased. There are other people who wrote their own libraries. They try to achieve the same goal, but I think we do it better. Okay, there is a GitHub link. There is a CPP cron video me and Joel Falcou did on it. Okay, and with this, I'm ready to talk about strlen, unless somebody has any questions.
What about Sickle?
Sickle, I never played around with it, but you know, I don't know what they do. If they just do LLVM stuff, they can't do anything but transform and transform reduce, because that's only the thing. Auto-vectorization works like pattern recognition thing. So you write scalar code, it recognizes what it looks like, and then it transforms into vectorized code. I think it works like that. Just judging by I'm playing around with auto-vectorization, so I don't know. I don't think they can do anything else. Maybe I'm wrong. Okay. So if anything else, and let's do strlen. So this is kind of the first thing that stumbled me about strlen is like, how in the world can you vectorize it? Because you don't know how many bytes you can load, right? You want to check for 0 in like 32 bytes at a time or something, but how can you know how many bytes you can load if every byte can be your last? Well, my first idea is that allocation happens in pages, right? So if you have a byte somewhere, you have the whole page for yourself. So the page is like whatever, 4 kilobytes on x86 and 16 kilobytes on ARM, I think, minimum page. So I might be wrong on ARM thing. And the second thing that goes from the first thing is that reliant addresses are safe. I'll show you what I mean. Okay, so this is a page somewhere in memory, right? And this is our string. Let's put some numbers on it, right? So this is the beginning of the page and the end of the page are going to be aligned to 4 kilobytes at least, right? And this is whatever, FDD, right? Let's align our address to, well, on my machine, I'm going to do to 32 bytes, right? What do I know about this address? Well, I know that this distance, because the beginning is aligned, this is aligned, is going to be divisible by 32, right? This is divisible by 32. It means that if I load by 32 bytes from here, I will either entirely land in the page, or I will not land in the page at all. Does that make sense? Okay, perfect. So it means that I can go by 32 bytes, check, and either, you know, if there is no 0, it means that the next page is also mine, and I'm okay going there. If there is a 0, I should stop because I finished my strlen. Okay. So now we can forget all about pages and just know that we can load from any aligned address as long as we have at least 1 byte there. Right? So I have my memory, and I have S string. I'm going to align S, and I'm going to load 32 bytes from there. Right. There is this primitive in Eve written with like 3 intrinsics. First true, it takes your 32 bytes, and you could well, with it you can test like where is my first 0, or it returns optional if there isn't one. Make sense? Right. There's a problem. This space between aligned S and S can have a 0. So the first true will accept and ignore, like it's like some types, tag types that will tell it, oh, okay, please ignore first n elements. Like, okay, I'm gonna check. Is there a 0? No, there isn't a 0. Going to go to the next one. Is there a 0? No. Is there a 0? Yes. And I'm gonna compute this distance. This is my strlen. Does it make a little sense? All right, sorry, one sec. Like, okay, let me do another one. All right, so this is a code of strlen written with Eve, right? Is it visible, okay? Yeah. So I have a string coming in. Because this is char, a char is a lousy type. It can be signed, unsigned, it can be weird. So we interpret cast to uint8, right? This is Eve's abstraction on top of a register, wide, right? So for my platform, it will be 32-byte register. Right? I'm going to fill in some zeros. This is just to test against. Compute the previous aligned address of my string, and then load from there. Then I'm going to do my first test. This is the first block where we had something to ignore. Between S and aligned S, we should ignore. Right? Then, okay, is there a match? While there isn't a match, we'll go and load from the next aligned 32-byte address. And finally, there is a match, we'll compute the distance. Okay, look at it for a second, and then kind of I'll move further. Okay. Sorry, and this. Right. Not quite what would strlen look like. There is a problem of dynamic analysis. Everything I said about pages is true, right? Like your operating system will not care. Your processor will not care. It's your page, you do what you want. Your C++, whatever dynamic analysis tool will care and will complain. In Eve, we have this primitive called unsafe load. It's just the same as load. It just has, all the attributes for Clang sanitizers. Yeah, I don't know how to make this work for Valgrind. Maybe it complains, maybe it doesn't. So this is a version of the code with, with unsafe load. And let's measure, right? So I use Google Benchmark. I have some way of dealing with code alignment. And I use 40,000, 10,000 bytes, as you already saw, for my data. I use 40 bytes because small sizes are important, and between 1,000 and 10,000 bytes, some effects can only be visible on 10,000 bytes. And I usually just char short and int. I don't test floats because just it takes a lot of time to run benchmarks. Nothing against floats. This is some numbers. This is on 40 bytes, our strlen versus standard strlen. We're about 2x faster. This is inlining, right? Nothing interesting here. On 1,000 bytes, we're slightly slower. There is actually a difference. And on 10,000 bytes, we're about 2x slower than standard strlen. Okay, why is that? Well, the thing is that we are underutilizing our CPU, right? We have multiple instructions we can execute in parallel. So let's unroll, right? If we unroll 40 bytes doesn't change, 10,000 bytes becomes 1,000 bytes becomes faster. It's a standard strlen. It's actually if you go to small sizes, it'll be a little more faster than standard strlen. And on 10,000 bytes, this is slower than the standard strlen. Why is that? So they are using multiple registers, slightly more efficient for bigger sizes. What they do is you load 32, 4 times the 32-byte registers. Then we're going to test all of them in parallel for zeros. Do an OR, do another OR, and then is there any matches, right? So this way you can do like whatever, all of this execute in parallel, right? So you have 1, 2, 3, 4 steps to get 4 times 32 bytes results, right? This is a good technique for general purpose find. For strlen, I don't think, because it slows you down on small sizes, and strlen is more important for small sizes. But anyways, I implemented it in just find, and so we can see this is find if, this is find unguarded strlen, like we saw before, and so it's slightly slower on 40 bytes than the strlen because it has to check the boundaries and stuff. But on 1,000 bytes, it becomes faster, and then finally on 10,000 bytes, it's slightly faster than standard strlen. I am like, it's a bit of different algorithm, like doing strlen, unrolling buffer bytes, and doing just find if. I know more. I know more that I can reach. I have the beginning and the end, and strlen doesn't quite do that. Okay. However, comparing against standard strlen is not very interesting. Standard strlen is very good. I'm not suggesting you rewrite standard strlen for anything production. What's interesting is to do a find, right? With some, like, for integers, let's say. We want to find an integer. So, okay, this is the while loop, like, so on the unguarded version. So for chars, this is about, for 40 bytes, this is about 19 times faster. Like, this is about the same as standard strlen, right? This is 4 times faster for shorts. This is 2 times faster for ints. I reiterate, we can find 40 bytes is 10 integers. We can look up in 10 integers faster, right? It doesn't have to be big sizes. For 1,000 bytes, this is what? 65 divided by 7, 9 times faster, right? This is 128 divided by about 16 times faster, which is 16 shorts, makes sense. And this is chars, and same goes for 10,000 bytes. Like, this is the strlen version, like, so without the right boundary. And this is a 40 bytes. So I have here SSE2 also implementation. You can see that SSE2 version, right, is going to be slightly slower for integers on 40 bytes, but I don't believe this is very going to be real. But everything else, yes, there is, like, IVX2 version is 9 times faster here. So yeah. Couple notes. So huge thanks to Stephen Cannon for explaining how to do strlen on Stack Overflow. And I'll just mention this. So, like, in order to use these tricks, like, your alignment has to be correct. This is just in general too. If you have int star somewhere in your C++ program, like, it's going to be aligned to 4 bytes, you have to maintain this in order for this to work. Okay. Any questions on strlen? Okay.
Sometimes when you want to vectorize, instead of going back to your alignment size and same thing from there, we usually do like a normal loop of the elements until the first aligned byte, and then we unroll the rest.
Yeah, loop peeling.
Yes. Did you check that? And is it, which way is better actually?
It depends on your algorithm. So okay, let me explain. One thing you can do instead of doing the ignore stuff, right? You can just do scalar loop, like while you don't get the to aligned address, and then do SIMD thing. So this is common. It's known as loop peeling. The problem with that is for Eve library specifically is that you have to write both scalar and SIMD version of the same code. So from the interface perspective, writing the same code twice seemed annoying, and so we decided not to do it. Whether it's faster or slower depends on your algorithm. If you do stores, it's going to be the loop peeling will be faster. If you don't do stores, if you just load, the loop peeling will be slower. At least on the perfectly predicted data. So in the micro benchmark, in a real world, you will not have such luck with branch predictors and stuff. Yeah, and there is a code in Eve. You can look it up and have a look. It has all the comments and stuff.
I've got a quick question.
I can repeat it.
Right. So when it comes to the performance, you've dealt with the alignments. But do you look at all? Do you do any kind of multiple dispatch depending on the expected performance of the architecture? Because back in the olden days, when SIMD code was mixed with non-SIMD code, things fell apart quite a bit. So if you would insert Eve code into non-SIMD code, the overall performance would be not so good.
So this is a code exactly like what the strlen does, and strlen is inserted all over the real code, right?
But fine. So sorry, because there's a second part to this. And in more modern CPUs, the cores may, probably will, underclock if they are running SIMD code.
That's not. Yes, the CPU. Can we do that at the end? I'd love to talk about it.
It's just, yeah,
okay.
Of course, because it's nice to have an abstraction in Eve, but it would also be nice if it would deal with the performance of.
The short answer is everything. So it doesn't do anything by default. You can control it, like, so you can tell it, I would like the. Can I do it in the end? Like it's like a few words I have to say about CPU.
Pardon.
Yeah, no worries. Okay, so let's do some more algorithms like reduce. Reduce is a C++ 17 version of standard accumulate. So take an array and add up all the numbers with some operation. The difference between reduce and accumulate is that reduce it requires the operation commutative and associative, and I'll show you why it matters. Yeah, so I mentioned reduce. You usually don't have to write yourself. Compiler will do it for you. It's just interesting to know how the algorithm works. Okay, so there are two versions of reduce. One is when you add up numbers to the same number, like int to int, and the other is when you have your reduction type being bigger, right? If you are afraid of overflow. So we're going to do the same type first. We need an abstraction first. We need this operation called replace, right? We have a register, and we're going to replace the bogus number, the numbers we don't want in it, with another values from a different register. And the second thing we need to do is we need to take a register with values, and we need to reduce it with a given operation. Okay. How does it work? This is an interface. So you have a range. You have an operation, and you have a 0 for that operation, right? So if you have a plus, should be 0. If you have a multiply, it should be 1. If you have min, it should be like max value or something like that. And then you have initial value also. We have a register. We have an array, and we're gonna have, as we discussed, we want to do unrolling. So we're gonna have 4 sums. I'm going to align a register. We're going to load the first value, and we're going to add it to the first sum, right? And then, we're going to add the second register, the second sum, third, fourth. Right? As you can already see, our values go into the sums in a completely arbitrary order, right? So, so the requirement of operation being able to switch elements around is very important. Finally, we're going to add all of those values together. And we're going to reduce y to produce one value from that sum. In this presentation, I don't talk much about the intrinsics, but reduce y with a custom operation is not really about intrinsics. Okay, if there is a plus, we will try to look up on ARM, let's say, there is an intrinsic that just adds up all the values in the register. But if it's your custom operation, there won't be one. So this is how you do it. You have your register, and there is a fundamental set of primitives to shuffle registers around. So we're going to take, and we're going to swap the first half with the second half, like C, D, A, B, right? And we're going to add them together, A, C, B, D, A, C, B, D, right? And then we're going to take each half, swap the registers there, and do the same thing, right? And that way we get A plus B plus C plus D. I'll just mention that it's not important here because it's done once, but this is logarithmic performance time, right? So you have, half and then quarter and then eighths and whatever, right, to do the addition. Okay. Now let's do reduce to different type. We'll need an extra primitive. A primitive allows you to specify whichever length of the register you want, as long as it's power of 2. So you can do, let's say, on my machine, the default is 32 chars, but we can do 16 chars. And there is a convert operation. So we can take, 16 chars and convert them to 16 shorts, so let's say. Okay. Let's say we have, again, our array. So this is chars and we want to add 2 short, right? I'm going to load, instead of loading by 32 chars, I'm just going to load by 16 chars, then convert them to 16 shorts, and add them to sums. Hopefully makes sense. Okay, so let's look at the numbers. So I'll just, on 40, there's no scalar baseline because the compiler, as I mentioned, auto-vectorizes for you, right? We can see this is 40 bytes. We're about the same everywhere. This is adding up chars to char to short, char to int. For 1,000 bytes, Eve is slightly faster. This faster comes from us doing the just loading the complete register and doing the ignore things, and the standard the compiler will do the scalar cleanup for you. And on 10,000 bytes, the scalar cleanup doesn't matter. We're just the same performance. This is shorts, roughly the same picture, and this is int to int. 40 bytes, 1,000 bytes, 10,000 bytes. Okay. So a couple of notes. Yeah, you can see no SSE2 or SSE4 benchmarks. While preparing the slides, I discovered that there's a better way to convert chars to shorts and ints. Like just so it's not a static thing. You constantly learn new things. It's not like you find the solution once. You kind of have to update it from time to time. And yeah, the second thing is like if you actually look at Eve's code, there's not going to be a replace. There's going to be this weird, scary construct. There's load, ignore, else. And the thing is that on some platforms, there is an instruction to do masked load, to load the values and replace the garbage values with whichever one you want in like one go. So we have an abstraction to kind of help us with that. Any questions on reduce? Looks good. Oh, hopefully not everybody's dreaming of beer already. Okay, next algorithm is inclusive scan. Again, the same version as reduce. It's a C++ 17 version of partial sum. You take an array and you add up the numbers and like 1, 1 plus 2, 1 plus 2 plus 3, 1 plus 2 plus 3 plus 4, etc. Standard one has an output array as a parameter, but in Eve there are 2 versions. There's an in-place version and there's a 2 version, because if there's an in-place, we can do it slightly better. 2 primitives, there's store, and there is a scan similar to reduce. You can scan register, so just compute the partial sums for register. I don't have an inclusive scan or exclusive scan because I didn't know how to make sense of one for a register. Okay, so inclusive scan works very similar to the previous algorithms. So we take, again, aligned value, load, replace with 0, do a scan. And well, for the first value, we can just write this thing back. But for anything further, you will have a running sum. So this is a running sum. We're going to add it together, and then we add it to store it to the output. And then we have to update the running sum. What is interesting here is that the speed up, it's not an embarrassingly parallel problem to scan an array. Your previous result depending on the next result. So the speed up comes from the ability to scan one register faster than to do it in scalar. This is how that's done. Sorry, I didn't update the title. It was like, it's really long to redraw them. So you have A, B, C, D, and you shift in 1, 0 on the left, and A, B, C, right? And add them together. You get A plus B, B plus C, C plus D. Then you shift in 2 zeros and add them together and get A plus B, A plus B plus C, A plus B plus C plus D. This is, again, a logarithmic operation, right? So you have 1, 0, okay. You have 1, 0, and then you have 2 zeros, and you have 4 zeros. So this is done in log. So the speed up we'll expect is something 1 over log. All right, numbers. So for 40 bytes, because the store with ignore is pretty slow, it just is not viable. So if you have really small arrays, it's not going to work. For 1,000 bytes, I'm going to remove SSE2 and SSE4. Let's see. So this is 54. This is about 4 times faster. 32 log is going to be about 5. So we expect is a 32 6 times speed up. 6 divided by 32 divided by 5. Well, it's 4 times speed up, right? Here it's about 3 times speed up for shorts and 2 times speed up for ints. And similar thing will be for and for 10,000 bytes. Couple of notes. So huge thanks to Zibazon on Stack Overflow for explaining how to do inclusive scan. And there's this instruction, like I just mentioned, there's a mask move U that seems like, masked store on x86. It's really bad. It was alone dominating the performance of inclusive scan. Just like, don't use it ever. And unless there are questions about inclusive scan, I will talk about remove, which is the last algorithm. Cool. Thank you for noting. I appreciate it. Okay. There's this monstrosity. It's just there's operation called compress store, and then there's a lot of variations on the compress store operation. This is kind of what it does, right? You have a register and you have a mask where the values are selected, right? So you have B, C, you want to F, G, K, right? Are selected. And then we want to store them at the pointer. And finally, it will return you where it's ended writing. And there is a little bit of garbage on the end if you allow it to be unsafe, right? Specifically, basically, if your register was 8 elements, in order to be efficient, I need to be able to write 8 elements, right? Otherwise, it's just not every time it's efficient. Yes, so there's this operation. It's kind of like remove for a register. And then with it should be, we have the safe unsafe compressed store, and the remove if kind of becomes fairly simple, right? We take the register, load. We need to select where we're going to write. There are 2 options. You can write where you have F, or you can write to the line F, right? I found that using the same address makes code roll out much nicer. Just keep the addresses parallel. So you load, test, and do compress store back. And this is updates out. And you load the next register and do the same operation again. Okay. Again, 40 bytes is not going to work. Like this is a scalar version at the bottom. Just writing the values or must store is too expensive. However, this is going to 1,000 bytes. SSE2 for chars, I cannot make it really fast for these values. However, everything else, let's see this one, for example. Right. So what's it going to be? This is about 4 times faster here, and this is about 4 times faster here again. However, the interesting thing comes when you go to 10,000 bytes, because your branch predictor stops saving the scalar version, right? And here we can see that even the SSE2 version for chars can do something. And when it comes to the maximum of what caching can do, like this is 50, this is 20, sorry, this is 24 times faster, right? This is removing zeros from array when there's like about half the elements are zeros, 24 times faster. This is also what Stephen as well mentioned, that there are no branches in SIMD code, right? So the performance is absolutely independent of how many zeros you really have here. And this is what, even there's 5% of zeros, this is 5 times faster. This is shorts. Again, really significant speed up. So this is more than 2 times faster. And this is more than a lot, more than 10 times faster. And similar situation is going to be for integers. Okay, couple notes on remove. There are 2 people who will enormous help. There's Akrit on Stack Overflow and Peter Cardes. And I'll just say there's, instead of library, there's remove copy. And in C++, so that was 1720, they wanted to have an unseek version of this. The problem with this is the interface that is a classic C++ interface with this O in here, right? It means that you don't know how many elements you have as the output, which means you can never use unsafe version, right? Which is unpleasant, right? I talked to Bryce about it. He is recommending to just copy the whole input array somewhere, or compute the output array somewhere, and then copy it to the result, which adds an MCPI, which sucks. Few general notes. So you can see there's a lot of speedups. Maybe I should have dwelled more into the numbers, but you know, orders of magnitude sometimes easy. I mentioned code alignment. This is a big problem for a lot of code. Problem is, like, depending on where your code is positioned, you have different performance. And problem with code alignment, and SIMD, it all comes from branches. SIMD has very few branches, really big instructions, so code alignment impacts SIMD very little. Again, you saw that data, like how many zeros we had in remove, didn't matter, right? Because there is no branches really. Aligned, unaligned memory access. I didn't talk about this much. Here we only used unaligned stores in remove. Everything else was aligned. It matters. Right, the instruction itself, so whichever you use, aligned load or unaligned load, doesn't matter. But the if you have aligned data or not aligned data, if you have aligned data, let's say you have 64-byte cache line, you load aligned by 32 bytes, you can fit 2 of those into a cache line. If you have unaligned, you can't. What did we cover? Multiple ranges algorithms. If can do them, like no problem, just didn't have the time. How to do set operations, some things are possible, some things I don't know yet, but like how to do merge, I know. How to do set union, not yet. How to partitions, how to do reverse. Floating point is like all done. In Eve, actually, we have a person who spent a lot of time doing math, so it can do sinus and like power and all that stuff. How SIMD participate, how SIMD and cache integrates. The thing is that with SIMD, you process data much faster. So if you're like, it can be often the case that you're out of, that you cannot just get memory fast enough. It's not even about being not in cache. It's just the prefetching is not fast enough to produce. Yeah, there's also gather, which is like, how do you do, like if you have arrays of structs and things like that, how do you load from multiple places? I just didn't study it yet. I seriously recommend you write strlen. Like you have all of the tools. Well, you have the headers, you have the explanation how it works, and it will give you a lot of understanding about how this works. Thanks to Joël Falco and Jean-Thierry Laprest who work with me on Eve. So those people on Stack Overflow. So Akrit, Peter Cardes, Ibazon, and Stephen Cannon. And the links, like there is a library, there is a talk. We have a Discord. We have I have some videos just on SIMD. There is a Slack, email, Twitter. Basically, if you want to use Eve specifically, or if you have questions about SIMD, I don't mind. Like reach out and I'll help you as much as I can. We wrote solutions to people, just like how do I vectorize this, and we just give them an answer. If it's simple, if it's hard, we will not. All right. So that's it for me. If anybody has any questions, I'm happy to answer.
Yeah, just have a question on the benchmarks to remove. So imagine the performance depends a lot on how many elements you remove.
So well, let's have a look. So this is on the X line, there is how many elements we remove, right? So the zeros, this is no elements to remove, 5% of elements to remove, 20%, 50, 80, 95, and 100, right? So it doesn't.
But that does it not affect the amount of data you have to work with?
No, you compress store every register. So for every element you load it, you do the shuffle to do compress and you store it. Like there is no difference. There is a difference on SSC2 because the algorithm does a switch. So let's see. On SSC2, you see it's not as balanced, like because it has to jump. It doesn't have the runtime shuffle. It has only compile time shuffle. There is a switch table, right? Because there is a switch, it's like a branch. It's data dependent. Everything else is not data dependent.
Thank you.
In your experience, how good was the performance of GCC versus Clang, for example, on auto vectorization, things like loop unrolling?
Yeah, so GCC doesn't unroll loops. By default, you need to tell GCC there is a flag F unroll loops, and still Clang is better. So I think that Intel engineers put in the effort to make it better. There was a question about the frequency scaling. Okay, let me explain the frequency scaling. So this is the thing, like you have big registers, like let's say 64 bytes on AVX512. And when you have the big registers, they heat up the processor more. So there is the thing that I don't know how to call, maybe you know how it's called, that is controlling the heat. And basically there is also, I'm not sure about the protocol, but basically what happens if your processor starts to heat up, it sends the request to the thing that controls the register, and then it gets us.
So on AVX processors, the top half of the circuit. On AVX processors, the top half of the circuitry is actually powered down when you're not executing AVX code. So it actually turns all the power off. So the first time you execute an AVX instruction, it starts to power up the high 128 bits of the ALU. That takes about 70 microseconds to occur. So for 70,000 nanoseconds or 200,000 cycles, it's actually emulating AVX via SSE by double pumping all the instructions in the microcode. Once it's up to speed, then it says, fine, I can now run my native AVX instructions using my wider arithmetic units that have powered up. But in the act of doing so, it's downclocked the chip according to the power license. Now, when it first came in, your typical 2.4 gigahertz CPU will be downclocked forcibly to 2.1 gigahertz. So it's now running about 10% slower. Now, after the CPU then detects it hasn't used any AVX instructions for about 700 milliseconds, nearly a second, then it powers off that circuitry again, and it lets the CPU speed go back up to full speed again. So the problem we had when we were doing this is running a benchmark or any kind of really intense loop works really well, but as soon as you throw it into general purpose code, you call your strlen function, it's emulated using SSE, the CPU runs slower for the next nearly a second, and particularly on the Haswell chips, that downclocking wasn't just on that core, that was on all the cores on the chip. So yeah, the newer chips are better and they thermal throttle better, and it's all about the turbo speed, but there's a definite penalty as soon as you start using the AVX instructions and AVX2. But Intel hide this stuff away inside their documentation because they don't want to tell you that, in fact, the 2.4 gigahertz CPU that you bought is actually only a 2.1 gigahertz CPU, and it's only running at 2.4 when you're not using the AVX, when you're not using those parts of the CPU. So
the way it was explained to me, right? Like it was explained to me practically exactly the same as you expect. I don't know how to formulate it that well. I don't know. But for me, it was explained that there is everything else except for, so like there is normal code, there is IVX2 floating point, and then there's IVX512 everything, right? And it's not even one instruction. So in our code, like we don't do HFT. I don't do HFT. In our code, IVX512, you have to do something really big. or like, you can use IVX512, it's fine, but you cannot use 64-bit registers. If you use 32-bit registers, you use this. It's not about instruction set, it's about how big your registers are. Yeah. So, or 16-byte registers. So in IVX, yeah, so in our code, we can use IVX212, like 32-byte, no problem. 64-byte, you have to do something really big. This is a big problem with Intel, with IVX512. It's only suited for really big workloads. Yeah, with respect to how Eve handles it, is basically we don't really at the moment. We just let, so there is you can, for every algorithm, there's a lot of parameters. You can control how much you unroll, you can control whether you align, and you can control how big, how many elements at one cycle you do. And so you can say, I would like to use only, 32-byte registers. By default, we do 64-byte registers on IVX512. Maybe we shouldn't, but the idea was that if people enable IVX512 and they see 32-byte registers, they will say, like, what the hell are you doing, right? It was just what people would expect in the interface. But yeah, absolutely. Thank you. And thank you for the question. Anybody else?
Do you mind offering a comparison with the other library, SIMD?
So when Eve was there before me, when I was looking into, I wanted to learn the SIMD. Like I didn't know anything, and I was kind of confused. So I looked into a few, like VC, TSIMD, XSIMD, NSIMD, for something else. There's a standard SIMD now. The problem with them, they were not really designed with algorithms. So like the only one like they do SAXPY. Like they show you, okay, we can multiply two registers at once. They don't show you remove because they can't do it, right? From what I have seen a few years back, right? Then I started writing my own thing, and then I discovered Joel with his Eve library. And it's not like Eve could do it. Like is that basically I came and said, if you help me, right, do you want me to use your library in my talk? Like then you help me, and I will bring the library to to the talk. And that was the idea. And then I spent a lot of time porting the algorithms to ARM. Now there's SVE and WASM and what the hell you. Anything else? VC could do find, some version of find, no unrolling, but nobody. Right.
Question then. What do you think is then the future of AVX512 with Intel? The older lake situation where the power cores and the economy cores, they've forcibly burnt the AVX512 out of the power cores. Do you think that?
Let me explain for everybody what the question is. So the AVX512 had the thing. So like we, for example, spend a lot of time buying the Rocket Lake chip just for the Eve library to run, because Rocket Lake has AVX512. And then there came Alder Lake, and in Alder Lake they had like two versions of cores. They had cores that had IVX512 and cores that don't. So you run the code, and basically you're half the half. It either works or it crashes, right? Something like that. And then basically they had this like idea that there's going to be programming model where you do that, and nobody did that. So they disabled the IVX512 forcibly, right? Like so, Alder Lake chips with IVX512 only in the chip, but it's disabled. What I think about the future of AVX512, I know that AMD now shipping. Then for like the print announcement that AMD doesn't support AVX512 before now, they're now shipping the Zen 4. And the interesting thing is that they actually emulate the AVX512. The AMD, as far as I know, they have this problem for a while that the cache line is 32 bytes. And when you have 64-byte registers and 32-byte cache lines, it doesn't really make sense as far as I understand. So what they do now is they emulate the AVX512 on the AVX2, right? So they have 32-byte registers, but the instruction will execute it twice. Maybe that's actually an answer to the clocking speed, because you get the twice as slow like clocking. I don't know, to the frequency scaling thing. I don't know if that's solved it or not. Well, I think, but since they're shipping, like great. They will be continue shipping, and people will write code against it. I don't know.
This discussion about whether Intel were trying to kill off AVX512 because it's so fragmented and it wasn't getting a lot of pickup, and then AMD sort of spoiled that party by shipping AVX 512.
I don't know. I heard the rumors that they're gonna kill it off. I don't know. But if you use Eve, you don't have to worry. You just anything else?
SV2 support.
ARM, yeah, ARM, Nuon, yes. SV, we just started. Like, it's a whole another can of worms. Like, I'm happy to talk about SV, but let's do it offline.
So you mentioned if you want to do floating point, you have to do fast math.
If you want to auto-vectorize floating point, you enable fast math. Yeah.
I don't. Can you elaborate on that? Like, what's stopping you from not using fast? Yeah.
So the floating point matter which order you do operations, right? Like because you have, like, if you, let's say, add up floating point, you want to start with the smallest ones and kind of try to do them balanced way because you accumulate the error, right? Adding a really big floating point with a really small floating point gives you the same big floating point. And so the question is, so it doesn't commute. And so the compiler is not allowed to throw your operations in random order. Fast math, so there are, honestly, there is a lot of things about fast math that I absolutely don't know. There's like special mode in the processor. Sometimes it enables. I have no idea what that's about. If somebody knows what that's about, I'm happy to.
Like the fast math doesn't guarantee accuracy. Like it doesn't absolutely guarantee bit reproducibility. So people like the Met Office will be very, very scared to. So I work in HPC, like high performance computing. So we work on research projects with the Met Office. So the first thing that they do is disable fast math because they want the weather models to predict reliably. So the same code should produce. So floating point operations are very tricky, as we all know. And the problem with fast math is they will not give you reproducibility. It's just the way the floating point operations, as you said, the commutativity and associativity must be preserved for floating point operations to work. So basically disable fast math.
For me, we do a lot of machine learning, like we don't care. Well, machine learning is a bunch of, like, I saw recently feature generation that was just a random number. They were trying to learn something from generating a random number. Like, it's just nonsense. Is it correct? No?
Okay, I think we're good.
Right. Thanks, everybody.